Okay, so today we'll be basically continuing with the session that we have continued. We have discussed on the name node storage. Okay, so let me just open a whiteboard and I'll be sharing that. So can anyone tell me, let's do some Q&A before we start. So which process is running on a master node as we discussed on the yesterday's session? Yes, that's absolutely right, everyone. So name node is running on a master node and data node is running on a slave node. Okay. Name node stores what information? And what does metadata contain? Yeah, what information name node stores in the metadata? That's right. Yes. Thank you, everyone. So basically, name node stores the information related to blocks and data node mapping. That means which block of the file is stored in which data node and which file is divided in how many blocks, right? So file to block mapping, block to data node location mapping. That is the information stored by name node. And what is the default size of the block? Correct. So 64 MB was the default size, but in latest version, it would be 128 MB. But that's fine. Any of this number is absolutely fine. All right, cool. So let's do this. We are basically going to talk about the way name node takes a backup of the FS image information, and we have discussed that all the metadata information. This is my name node. So this, let's say here I am storing all the metadata information like file to block mapping, block to data node mapping. And we have discussed that name node keeps all this data in the main memory in the RAM of this machine where the name node is running, right? Why it keeps this in the memory? Because when clients are trying to access the file information from the Hdfs, name node will basically check whether it has that information about that file which client is asking to read from the metadata. Now, always name node has to respond to every client request, and it is possible that there may be many clients who are running on Hadoop cluster. That means many jobs running on Hadoop cluster who wants to process the data, and hence name node will basically check whether I mean, basically it's not about checking, but it has to give the response to the clients by looking at the metadata information, and that's why it is important for name node to understand that it has to respond it very fast. It can't take too much time to respond it because most of the jobs are waiting for it. And to do that, instead of reading it from the file, it keeps all the data in memory so that response will be faster. Otherwise, it has to open the file, read the data, close the connection with the file for every request, which is time-taking activity. Okay, so basically, Nimnode keeps this metadata in the RAM. Apart from that, since if you put all the data in RAM only, then also there is a problem because if Nimnode crashes, you will lose all the data, right? So to avoid that, it will also store this data physically in the local machine under the file called fs image. Okay. Basically, all this data from memory, it will take a backup of them periodically and dump it into the file called fs image in the local file system of this machine, of the machine where Nimnode is running. All right. Now we have to understand how does it take a backup. So every 24 hours, that's a default time period where Nimnode takes a backup from metadata which is stored in memory into the fs image, right, which is basically stored in the local file system. So for example, let's say I have a file which is stored in this location. Let's say it wants to take a backup, dump all the data from memory into the fs image. So every 24 hours it does. So let's say now it is doing that. It has created an fs image with some version and it dumped all the metadata into the fs image. Now after 24 hours only it is doing one more backup, right? It will create one more fs image file. This is 24-hour operation. Okay. So after 24 hours it is taking the backup. But if you observe here, even this 24 hours also, your cluster is operating. That means, Nimnode is live, all the processes are live. And hence, if any changes that is being happen on the cluster, that means on the Hdfs. When I say change, what could happen? A job can actually add a new file, and the moment a new file will be added in Hdfs, the Nimnode might increase the storage, increase in the sense might change the metadata information in the RAM. Right? The moment you are adding a new file in Hdfs, what happens? It will be creating new blocks. So that information have to be updated in the Nimnode's metadata. Right? Likewise, if there is a file which is being deleted from the Hdfs, then also Nimnode have to delete that data from the metadata, right? From the memory where it is keeping that. So all the changes are also being recorded in the Nimnode's metadata in memory. So for example, if at this point Nimnode crashes, okay, then all the changes which has happened from the last checkpoint to this point in memory are lost, right? Because we are not keeping a backup of those changes, because we will take backup only after 24 hours, right? So obviously there is any change which happen in between are lost. So to avoid that, Nimnode keeps backup of those changes into a new file called edits file. Okay. So what it does, it will take all the records and understand wherever changes has happened, and it will take up those records and then put it in the separate file called edits file, which is also referred as an edit log file. Okay. So as and when some changes happen in the Nimnode metadata, that change is being recorded in the edits file. So people who want to compare it, you can compare it with redo logs in the Oracle database. Okay. So all the changes will be recorded in edit. So now in this case, I will have all the updates till the next checkpoint. I will have all the updates which could happen in metadata being recorded in the edit file. Now what happens in case if at this particular point name node goes down? Even though you have recorded all the changes in edit files and you have till last checkpoint you have the FS image file copied in the hard disk. But then at this point if it fails, then we have not yet merged these two files, right? If you don't merge it, then what happens? At this point, if name node have to restart, it has to read data from the FS image, but it can read only the data till last checkpoint. All the changes which were happened were recorded in edits file. So we have to also apply all the changes to old FS image to make it the latest FS image till this point, right? So basically, that merging has to happen because at the next checkpoint, anyway, all the metadata would have been dumped into new FSMH file. But before that happen, only name node crashes. So we have to also make sure that there will be a merging that has happened so that periodically FSMH data will also be kept up to date at any point. So that if name node crashes, it will still have that FS image and it will load the data from the memory, right? So this process where you do merging of FS image and edit file is called checkpointing process. All right. And we are going to understand how checkpointing process works. Before I explain that, is everyone clear as of now? Any questions on this? No, Vishal, it doesn't replicate because it is stored in the local file system. It is not stored in the HDFS. So there is no concept of replication which happened here. Okay, is it clear, Vishal? All right, so now let us understand how does the checkpointing happens. Yeah, Raj, that is configured. Yeah, that's what I said. I understand your question, Raj. So yes, it is configured. That's right. No, Vishal, there will be a new entry. Oh, you mean to say in FS image? Okay, in FS image, I mean, basically, it will be basically updating the file. It will not be a new entry because in metadata you are updating that information, so that will be recorded in edits file, and that edits for information you are applying on FS image later. That is called checkpointing, where it will go and update the old data. Because that file is stored in local file system, you can always update it. No, Raj, there is no concept of rollback here because it is not a transactional storage. It's a file storage. All right. So we understand what goes in edits, what goes in FS image, right? So the edits file being transferred to the secondary name node. So secondary name node is one process as we understand in the cluster, right? You have name node and data nodes, right? And there is one more process called secondary name node in the cluster. Now secondary name node, remember one thing, is not a backup of the original name node. It is just there to do some kind of operation which is called checkpointing, where it helps you to merge the edits image with FS image, and it will take the backup of the FS image in a separate machine. So that if physically name node crashes with the hard drive, then also there is a backup of the file available with the secondary name node. Okay, but if name node fails, secondary name node cannot become active name node and start serving the cluster. That is not possible. So that is why, I mean, it is important to understand about the secondary name node. So because the name of that process is called secondary name node, which is little confusing. People tend to think that, it is a backup of name node, but it is not. It just helps you to do the merging between the edits file and FS image. So what happens here is, no, Mano, it will be basically periodically happen. So there is a configuration time between which all edits in FS image will be merged parallelly. Okay. So we understand what goes in edits and what goes in FS image. So what happens is it will apply all the edits information on the FS image. Now this is how merging happens. So let's say if you have some file, edits file, right, which has certain records, and you want to apply it on the FS image in file. FS image obviously will have a JSON kind of storage. So you want to apply edits into the FS image. This is the edits file. Mary, JSON is basically a separate file format just like XML, which stores the data in the form of keys and values. Okay. So here what happens is, see, when you want to apply all the changes, see, edit file can contain so many changes, so many records. So what it does is it will read one record from edit file, go and apply that record to the FS image. Let's say it finds out that this is the portion where it has to update it, so it will go and update it. Then it will go to the next record, again apply the same change into somewhere else in the FS image. Likewise, it will go to each and every record in the edit file and then apply that change to the FS image and make that FS image as the latest FS image file. So that is what we mean by merging these two files. So these two files will be merged and it creates fsimage.checkpointing file. Basically, a new version of the FS image will be created by merging these two files. Okay, and this file will be sent back to the secondary name node. Sorry, to the name node, primary name node. The primary name node will have now the latest FS image created after having these two files merged by secondary name node. Okay, that is how the latest FS image will be created. Now here, To apply all the changes from edit file to the FS image is a very lengthy process. It is not very, just like in a couple of minutes it will not be done. It may take a couple of hours, depends on the size of the cluster and the size of the data. So this process where you are merging edit file into FS image might take, let's assume couple of hours to create the latest FS image file. Till this point, right, when it is merging these two files and creating a latest FS image, even till this point, name node is busy, and it is, because your cluster is operating and you have to serve to all the new requests. So because old edit files are already being used, it has created a lock on these files. So name node cannot write any information on these edits. Then where does it change that? Where does it store that newly changes that has happened in the metadata? So what it does, it will create a new edits file. Okay, edits.new, or it is also called as edits in progress file, basically. So it will start recording all the changes in this file. Now what happens after these two files being merged? We have a latest FS image file and latest edit file. Okay, so we are back to the same place where we have started. Okay, now again this process repeats endlessly, so that again periodically these two files is going to be merged into the latest FS image, and this process is going to happen in a continuous manner, periodic manner, so that every some periodic time we will have these two files being merged and we'll have the replica copies, latest FS image copies created. All right. So, I'm sorry, I think by mistake it has zoomed it. So is everyone clear with this process, checkpointing process? How does the merging happens? There is nothing like max size of metadata, Vishal. It will be always just like a log file. It will be just dumping the file data, and then as and when periodic changes happens, it will dump it into the edit file. So there is no restriction on the max size of the file. Mary, we don't just understand this is a framework, so we don't really do any changes here, right? It is internal to the Hadoop framework. This concept is very internal concept to Hadoop framework. I'm just explaining you so that you will have an idea how does it happen. All Hadoop framework will do all this job. We don't need to do anything. So Mano, if name node goes down, once it restart, right, it needs to rebuild all the metadata from memory. When it wants to rebuild the metadata from memory, that time it will go and check this file, latest FS image file at that point which was created, and then start reading all the data from that file and then load it into the memory, and that's how it rebuilds the metadata into them and start serving the cluster. Okay. Yes, Vijay. This is a complete black box to us. We don't really need to know, but I'm just giving you an information. We don't need to take care of any code in this for this checkpointing process. Vishal, secondary name node need not be a high performance machine. It just needs to have some configurations which is little better so that it can do this operation faster. Doesn't need to have a very high end configuration like name node. Shiva, because if you want to merge, see, if you don't keep edit file as a backup, and if you want to just keep dumping all the data into FS image, then it will be a very costly operation, because every few seconds there is a change that happens in metadata information in memory. Every now and then if you want to go open the file, update the file, FS image will be very huge file. So that will be a performance overhead, and that's why they just record the changes in the edit files, dump that, and then only periodically it merges it so that it can save that performance. Mano, I hope you are clear with what happens to name node, right, when it is down. Yes, yes, Mary. All of the things which we are talking here is happen automatically. Guys, understand everything. One important thing. I am going to explain you internal architectures and the internal details. Developer does not need to do even one person job here. He doesn't need to take care of anything here in the code. Everything is completely black box. I am explaining you because as a developer you should have internal knowledge of your Hadoop system, right? Yes, Nikhil, your assumption is valid. Raj, I will explain about the standby name node. So, all right. So where does standby name node comes into picture? Yes, Nitin, that is a correct summary. Vijay, as and when there is a change happen in metadata, the edit file will be, it's not updated. Edit file, there is a new record which is being appended to edit file. Yes, Mano, standby name node is different from secondary name node. Yes, Vijay. As I said, as and when the changes happen on metadata, immediately the changes will be basically recorded into the edits file. These changes will not reflect in secondary name node. It is happen on the name node where you are creating new files. Secondary name node just takes the at one particular time whatever is the edit file you have, it takes that file, merges it with the older FS image file and create the new FS image file. So changes are not going to happen in SNN, secondary name node. All the changes are happening in the edit file created in the name node. Yeah, to answer your question, Raj, see, in the latest version of Hadoop, you have multiple processes like active name node and the standby name node. There is a secondary name node. So what happens is, if active name node goes down, the secondary name node cannot become active. It just helps you to do checkpointing process to merge edits and FS image. So that means it is still a single point of failure, right? Because I lose all the metadata information. Nobody else knows about metadata. That is a single point of failure in Hadoop 1.0 cluster. But in Hadoop 2.0 architecture, they have made an option available to have a backup name node, which is called basically just like active name node, you have something called a backup name node, which basically helps you to do all these operations. So there is a backup name node, which or you can say a standby name node, which is also connected to all the data nodes in the cluster, and the name nodes are also connected. But there is one active and one standby name node, right? So standby doesn't do any response to any request by the client. It will be just standby, but it remembers all the metadata information just like name node. Now active name node, when it goes down, standby will automatically, it fails over to the standby and it becomes active and starts serving the cluster. Is that clear, Raj? Okay. So now let's start understanding about. Yes, Mano, standby name node is optional. You can create a standby name node if you want high availability of the name node. That's what we discussed, right, Raj? So basically, if name node fails, it will definitely fail over to the standby name node because both of them are knowing the metadata information. There is a shared directory where both of them are storing the metadata. So even if active fails, there will be a standby name node will have access to the the metadata from the from the secondary name node, and hence it will always read up from there and start building metadata into the memory. So there is no problem. This is what I have shown, Vishal. Okay. Yes, that's right. Standby name node will always get a heartbeats from data nodes. So when you do failover, it becomes very easy to do the failover, and standby will immediately take the action. It will not be too much delay. Is that clear, Vishal? All right. So let me move forward. So now we are going to understand one architecture called write architecture. Like how do we write the data into the HDFS? That is the very important topic which we are going to understand in a detailed manner. Again, first thing I have to make sure, because I think a lot of questions have come related to that. These architectures are internal, developer doesn't do anything here. It's internal, it is taken care by the Hadoop framework only. Yes, Vijay. So that's a very good point that you have mentioned. I will actually address it once we cover this architecture. I'll come back to that. Hold on to that question. Mary, there will be a heartbeat signal being exchanged between active and standby name node. So the standby aware that active is available. If active fails, then standby needs to know, right, that it is failed. That is the communication that happens. Okay. Is that clear, Mary? I would request people, if your question is being answered, right, just acknowledge that it is clear or not, because it clearly helps me to move forward. Otherwise, I'll be in a dilemma that whether you understood it or not, right? So I request everyone, please do that. Some of the people are already doing it, but it really helps me to move forward. Okay, so let's say you have a file and I want to write that file into HDFS. The core architecture of Hadoop that I'm going to explain you. You will not find what I'm going to explain you in any material Forget about simply learned material. Even on the net also, it is very difficult to find this architecture in that level of detail. In the book, I have in fact given you the book on the first day itself. I have given you the name. I'll write it again if you want. If you want to read anything about the Hadoop. Hadoop Definitive Guide, 4th edition. This is the book. The author name is Tom White. So even in that book also, it is not explained to the great extent. Yes, it does have all the details. So what I have done is I have taken that architecture from the book, as well as I opened some of the Hadoop APIs. If you open the source code of Hadoop, you will get to know what happens internally. You have to go through all the APIs and all the flows. But that is what I'm going to explain you here. So it will be really interesting. So when you want to copy a file from local file system into Hdfs, what will happen internally? So you as a developer will just execute this command, Hadoop fs -put. -put means to copy the file from source location to the destination location. Now this destination path will be an Hdfs. Okay, so you can give any directory name here, and you can say I want to copy a file called file.txt under a data directory, right? So basically what would happen, you are basically going to copy a file from local file system into Hdfs under this directory /data/f.txt. What is // means root. So even in Hdfs, which is a virtual directory, virtual file system, it will still have a root directory, and under that only you will create files and folders and store data inside that. Right, so I'm going to store this data in this particular location. But as a user, I am thinking that I'm going to store entire file in this location. But what happens behind the scenes? It will be converted into physical blocks, and the block will be stored in the multiple physical machines. Correct? That is what we have learned. Right? In multiple data nodes, these blocks will be stored, and name node updates the corresponding metadata. So let us understand that in detail how this process is going to happen. So behind the scenes, what happens when you execute this command? For us as a developer, we are just executing one line of code, but behind the scenes what happens is what we are going to understand. So I'll just explain you that. So the first step is, see this, okay, by the way, this command that you are executing, you can execute it from any of this machine. The name node or data nodes. Okay, this command you can execute it from any of the machine, either from the name node or from the data node. Right, all these 4 machines in your cluster, anywhere you can execute. So wherever you are executing this command, that machine becomes a client for your architecture. So the client internally, see this entire command, see entire Hadoop is written in Java. So this entire command that we are using in Hdfs are basically written or implemented as a Java programs only, right? So internally it will call a Java program, and what happens in that Java program in as a step by step, that is what I'm explaining you here. So the client will make a call to the distributed file system object. There is a Java class which is written, which is called distributed file system. It makes a call called create method call on DFS. Okay, DFS is a Java program written by Hadoop framework. Why does it need to make a call on DFS? Because if you have done database programming using, let's say, by calling it from Java or any other programming language, you will know that if you want to talk to, let's say, RDBMS like MySQL or Oracle database or SQL Server or PostgreSQL, you need to have a JDBC ODBC driver corresponding to that database that you can actually call it through Java. So that's an entry point to connect to the database through Java application. Similarly, this is also one Java program, and through that you are going to connect to the Hdfs, which is your name node and data node combination. So that is why DFS is one class which is written by Hadoop framework which know how to talk to the Hdfs. So when you call this method, DFS internally will know how to go and talk to the name node. Name node will be running in a separate machine. When the DFS makes a call to name node will identify that how many blocks are there and all this information. So basically it will be something like this. It will make a call to the name node, and it basically identifies. It will first the DFS will make a call to name node, and it will tell name node that there is a client who is going to write a file in this particular location in Hdfs. Okay, so name node does some validation first. What it does, it will first go and checks it in the metadata information and tells that whether this path exists in Hdfs or not, whether this file already present in Hdfs or not. Why does it check it? Because if it is already present in Hdfs, then name node will not allow you to rewrite the file on the same location. Remember, write once, read many times that we discussed. In Hdfs, it's write once, read many times. So once you write the data in Hdfs, you can't update the data or overwrite the data. You have to first delete the file, then only rewrite the file. So that validation will be checked first. Once the path does not exist, then name node also checks whether the client will have a write permission to write the data in this location. Once these two validations are done, name node will send a signal back to the client saying that yes, I am good. You can go ahead and write the data further into the Hdfs. Okay. Once the name node sends this signal to the Hdfs, then to the client basically, the client will also get a new object called fs data output stream object. This object will be a return type of this create method. At the end, it will return this object. So client will now know that how there is an object given through which it is going to write the data further into the Hdfs. So from next step onwards, client will directly make a call to the fs data output stream object to write the data further into the Hdfs. Okay. Now why fs data output stream object is needed? Because if you see here, whenever you want to write any data into the data nodes, you need to have an output stream object created, right? Just like your input stream, just like your file IO programming. If you want to write the data into the file, you need input stream. If you want to read the data, you need, if you want to read the data from file, you need input stream. If you want to write the data into file, you need output stream. Similarly, you are writing a data into Hdfs, so they have created wrapper over the output stream, which is called fs data output stream. Again, that's a class written by Hadoop framework, which is given to client. Client is directly making a call on this class to write the data further into the Hdfs. Okay. So now let's understand what happens when directly client makes a call to fs data output stream, and how does it internally write this file and creates multiple physical blocks into the data node. This is just a first step that is completed in this architecture. So are we clear with this first step? Any doubts anybody has? Yes, Nikhil, that's right. Only first time. After that, it is going to call the fs data output stream. Yes, Shiva. Create and write are two different functions available in two different classes written in Java. Okay. All right, Mary. So let me repeat it. So when you write this command to copy the file from source location, which is your local file system, into the destination location, which is your HDFS. When you execute this command, behind the scenes, what happens is what we are going to understand, which is called write architecture. How does the data gets written into the HDFS? In that, first step is client. Wherever you execute this command from any of this machine, that becomes your client. So the client will make a call to create method on distributed file system object, which is a Java class, which know how to talk to the name node. So it will make a connection to name node. Name node will basically does some validation first, whether this file where client is going to write the data, whether it exists already in HDFS or not. If it already is existed, then name node will not allow you to rewrite the data because it is write once, read many times. After that, name node also checks the access permission that the client has to write the data into this location in HDFS. If the client does not have any write access, then he will not be allowed to write any data further. Once those checks and validations are done, successful, then name node sends a signal back saying that I am done. Then client will get a new object called fs data output stream object as a return type of this create method. This object will help you to write the data further into the HDFS. So client will now make a call to fs data output stream object to write the data further into the HDFS. So is it clear, Mary? And all the other people who have asked their questions, I hope you are also clear. All right, so let's go to the next step, which is client is directly making a call to the fs data output stream. So I'm just going to rewrite this architecture. So I'll just quickly rewrite some information and I'll draw some boxes, then we'll start talking about that. Let me first draw this, then I will explain you what I'm doing here, okay? Alright, so now let's start understanding what is happening. So as we discussed, the next call is client is making a write method call on the fs data output stream object, correct? So what is happening in that? So when client makes a write method call on fs data output stream object, the fs data output stream object is going to write the entire data into the Hdfs in the form of blocks. So what does it do first? It will basically create three instances: data queue, acknowledgement queue, and data streamer under the Hdfs itself. Okay, it is going to create three different instances of this queue. I'll explain you what all these components means and what does it do. Right now, assume that there are three instances which are created into three different into the memory of the machine where fs data output stream is running. Now what fs data output stream does is to write the data, it knows that this is the source location where the data input data is available. So it will have one property which is called dfs dot write dot packet size. dfs.write.packet size. So the default value of this is 8 MB. Okay. You don't really need to change it. It is configurable, but no need to change it. It will be always default. So what happens is fs data output stream object first goes and picks up the source location file and tries to divide that file into 8 MB packets. All small 8 MB packets it divides your file into. Now assume that default size of the block is 64 MB. See, when you have a file stored in the local file system in the source location, your file is not converted into blocks, right? There are no blocks created. It's one simple file only, but its size is 128 MB. But if I store that file into Hdfs, considering 64 MB as a default size of the block, it will create two blocks, right? So that is what fs data output stream is going to do. So it is actually first dividing the file into the 8 MB packets, and then it is basically going to read those 8 MB packets, like first 8 MB packets, for example, which first 8 MB packet, because 8 into 8 is 64, right? So first 8 packets will be loaded into the data queue like this: P1, P2, P3, P4, P5, and so on and so forth. Right, like that there are P6, P7, P8. These 8 packets are loaded into the data queue. Okay, that means it knows that it is going to write one entire block into the Hdfs. You may have a question, what happens to the next set of 8 blocks? I will explain you that later. Let us understand how one block gets written successfully into the Hdfs. Okay, so these packets are loaded into the data queue. Now what data streamer does is it will go and pick up the first packet from the data queue and it starts writing that packet into the Hdfs. So what data streamer does, it will first pick up the packet from data queue, remove it from data queue and put it under the acknowledgement queue. Okay, and then it wants to write the data into the Hdfs. When I say it wants to write the data into Hdfs, ultimately it has to write it into the data nodes, right? So data streamer does not know which location, which data node it should go and write the data. So for that, it has to ask this information from name node. So it will go and ask this information to name node that can you tell me which all data node I should go ahead and write this packet. Okay. So name node actually name node will basically check this file and then see in the first call name node was already aware of that there is a client who is going to write file in this path, right? So he has already registered this entry in the metadata. Now when you are when the data streamer is asking about data nodes, name node gives him, after checking, let's say there are 10 data node in the cluster. After checking that, let's say it finds out that there are 3 data node where you should go ahead and write the data in these 3 data nodes, because they are the best possible data nodes that client should write into at that point of time, right? It does all the node balancing. It checks which data node is more free, which data node is closer to the client. All these parameters are considered, and based on that, 3 best possible data nodes are selected and given to the data streamer to write this data. Okay. Along with that, name node will also give him one block ID, block 001. What is this block ID? I will tell you later. Right now, just assume that there is some block ID which is given. Okay, and parallel it also updates the metadata. So data streamer now gets the information that these are the 3 data nodes where I should go ahead and write this packet. Once it gets this information, it starts writing the data into the data node in this order. Okay. Now, before we understand how does it write it, is everyone clear to this point? Any questions on this point? Yes, Shiva, data will be removed from data queue and put it into acknowledgement queue. So, Shiva, are you clear with your question? Hello, am I audible, guys? Okay. So I just asked question to Shiva. Shiva, are you clear with the question that you have asked? Okay. No, Vijay, he just mentioned that if the packet is removed from this data queue and then put it in acknowledgement queue, or it will be still there in data queue. So I said yes, it is removed. All right, Raj actually explained me to repeat this, so let's do that. Let me repeat this flow which I have explained so far. So we have basically this architecture where client is going to make first step we all have understood, right? The next step is client is making call to the FS data output stream object to write the data further into HDFS. So client is making a write method call on fs data output stream object, right? And in that, client is basically going to create three components: data queue, acknowledgement queue, and data streamer. Right? Data streamer is a thread. I'll explain you what does it do. So basically, fs data output stream will go and pick up your file from the source location, divides it into multiple packets, and the size of the packet is being taken from this property in one of the configuration file, which is 8 MB. So it will accordingly divide your file into 8 MB chunks, and it will read first 8 MB into the data queue because it wants to write 64 MB block. So it needs 8 packets of 8 MB size. So it will load first 8 MB packets into the data queue. Now, data streamer is also one more component which was created by fs data output stream. So it is nothing but it's a thread. So thread will be running. It will pick up the job from the data queue and start processing it. So what happens? Data queue will go to and pick up first packet from the data queue and put it in the acknowledgement queue. I'll tell you what is the use of acknowledgement queue later. But let's say it puts it into the acknowledgement queue, and then it starts writing the data into the name node. Sorry, into the data node. I'm sorry. So, but to write the data into the name data nodes, it needs to know which data node it should write, and to get that information, it contacts name node. Name node will do lot of important filtering, or basically it does check all this information, like out of, let's say you have 10 data nodes available in your cluster. Out of 10, which 3 are the best possible data nodes in terms of load balancing, which means resource consumptions, which are 3 more free data nodes available compared to others. And then it will also check the distance between client and the data nodes in terms of proximity to client, and then it will basically present those data nodes to the client so that client can directly write the data into the data nodes. Okay. So that's clear, right? This flow. Now data streamer will start writing it into the data nodes. We'll understand that part now. Okay, along with this, the name node has also given him one more information which is called block ID. And we'll understand what is that. Now I have a question for all of you. Why name node has given 3 data nodes to the data streamer? Why it has not given 2 or 4 or 5? Why only 3 data nodes are given? Yes, very good everyone. So 3 is the replication factor. That is why name node has given him only 3 data nodes. That's a default replication factor. So what happens now? Data streamer will start writing the packet into this data node. So it will take first packet, goes to the first available data node, and then it will create a file. See, remember we were telling that if we have a file in Hdfs, we store it in that. If we store that file in Hdfs, what happens? That file will be divided into multiple blocks, physical blocks, right? And then we used to tell this that at every data node machine, the blocks will be stored like A is here, B is here, like that. These are data nodes, these are name nodes. But what does this mean? These blocks are also physical files only, right? So your physical file is divided into 2 different small physical files and store the data into these data nodes. So when you have a file created automatically by framework, obviously it needs a unique name, right? So that it can store that file. So that unique name is nothing but a block ID. Okay. So since Hadoop framework is maintaining the creation of this file, it gives a unique name to this file, which is called block ID. So even the blocks are also files only. So it creates a file with this name and stores So it writes packet P1 under a file called block001. Once it writes this packet, data node 1 sends a signal to data node 2. This is where data node communicates with each other, and data node 2 will also write the same. It will create same file block001, and it will write the same packet called P1. Once that packet is written successfully, then data node 2 will make a call to data node 3, and it will also write this packet under a new file called block001, and that packet will be written successfully here. Once data node 3 writes the packet successfully, it will send an acknowledgement back to data node 2. Data node 2 will also send an acknowledgement back to data node 1 that I am also done writing this packet. Once that acknowledgement has been given to data node 1, it will send it to the data streamer saying that yes, this packet has been written successfully into all the 3 nodes. Okay. Now once that acknowledgement has been I'm sorry, I didn't get your question, Shiva. Is this also a replication? What does that mean? If you are asking about this, yes, it is a replication. So this block is created 3 times into 3 different data nodes, and the packet is written 3 times. This is a replication. That is why we got the 3 data nodes. I will explain you that later, Nikhil. Because of the failure scenario, it becomes very difficult to manage which packet is failed for which data node writing. That's why it writes packets into sequential order, so that it exactly know which packet is failed at which level. Okay. Alright, once the acknowledgement has been received by data node 1 to the data streamer will move the packet from acknowledgement queue. So that means if the packet is successfully removed from acknowledgement queue and data queue, that means it is returned successfully into the Hdfs. Then data streamer will go and pick up the second packet from the data queue, put it into the acknowledgement queue. Okay, and then it has to write this packet P2 into the data node. Now here I have a question for all of you. To write the second packet into the data nodes, does data streamer have to go to the name node to get all the data node location where it should write this packet, or it can directly start writing the packet into the earlier data nodes which was given to him? What should it do? I think some of you have already given the correct answer. So basically what it needs to do is, it doesn't need to go to the name node to get this information further. Why? Because already in the first call, name node has given you the list of data node where you should go and write the data. And till you complete 64 MB data, that means till you complete all 8 packets writing into the same block, you don't need to go to the name node to ask more information. Right? Name node has already given you that this is the block ID where you can go ahead and write the packet. So there is no need of going back. That's why packet P2 will be directly straightforward written into the same file in this 3 machines. Okay, and the same way, packet P3 will be written, P4, P5, all of them are written here. It doesn't matter, Shiva. They'll be writing it into the different file. So don't worry about other users. They will be writing into the separate file, not into the same file. So Vijay, it will know when all the packets, all 8 MB packets from data queue are written fine. All 8 MB packets are written fine. Then only it will know that yes, the block writing is completed. So the last packet, which is P8, when it is written, data queue will be empty, and that time data streamer will check if data queue is empty, data acknowledgement queue will also be empty. Then it will go and update the status to the name node saying that yes, I have written this block successfully. So name node has parallelly built a metadata which maintains this information that the file to block mapping, and it will also maintain this information that this block 001 is stored in which all data nodes. So it will say data node 1, 2 and 3, right? So parallelly the metadata information will also be updated by name node. So that is what happens when we write first block into the HDFS. We have not yet covered unhappy path scenario, which is basically what happens in case of any failure happens. I will cover that separately. Okay, this is just a happy path scenario, which means if we assume everything goes fine, then how does it write one block? So we completed understanding how one block gets written successfully into the HDFS. Now I am going to explain you how second block will also get written into the HDFS. But before I do that, is everyone clear with this one block writing? Any doubts anyone has? So Nikhil, latest Hadoop version will have 16 MB as a packet size and 128 MB as a block size. So it will be the same logic only. That's because Nikhil, you have to complete writing one block. That's why 8 packets of 8 MB size are loaded in data queue. So that total 64 MB data can be written in one block. No problem, Nitin. Since you have missed few minutes in between, I think just for your benefit, let me just repeat it quickly. Uh, I'll just give you overview. If you still did not get some information, then yes, as you said, please rewatch the video because that will really help you to understand in detail again. So I'll just repeat this entire step, okay, for everyone's benefit. What we have done is, client will make a call to FS data output stream object. The FS data output stream object create 3 components: data queue, acknowledgement queue, and data streamer in memory. Then FS data output stream knows that I have to write this file from the source location into HDFS. So it will read one property from one of the configuration file which is dfs.packet size, which is 8 MB by default. So dfs.write.packet size will be taken and it will divide the file into 8 MB chunks. First 8 packets of 8 MB each will be loaded into data queue because yeah. So because it has to write one block in the completely into the HDFS, it has to first load only 8 packets of 8 MB size so that it completes writing 64 MB data. Now what happens, data streamer will go pick up first packet from the data queue and put it into the acknowledgement queue. And then it will go to the name node to get the location of data node where it should go ahead and write the data. Name node will give him that these are the 3 data node, you please go ahead and write the data. It will select the data node based on the load balancing and the proximity to client, which data node is closer to the client, so that it improves the performance by writing the data. And then data streamer will basically write that packet P1 into all the 3 data nodes in a file which is called block ID, which is also given by name node. Once the packet P1 is written successfully and acknowledgement has been received by all the data nodes, data streamer will remove that packet from the acknowledgement queue. Then it moves to the writing the next packet from the data queue, put it in the acknowledgement queue and start writing it into the data nodes. Under the same file, it doesn't need to go to the name node because still the block is not yet completed. So under the same block, it will write packet P2 also. Likewise, this cycle continues till packet P8 is written fine from one data node. Okay. So once the packet P8 is written in data node 1, 2, and 3 successfully, then it will basically write the basically all the packets are written from the data queue completely, and that means it will inform the name node that your first block is written successfully. That's what completes one block writing. Okay, no problem, Nitin. Thank you. So by the way, this kind of internal informations will not be achieved in any of the session, probably from any other books or material, because as I said, right, this is very internal discussions that you can only get to know by reading the code or some books. So that's why it's important to rewatch this video whenever you want to clarify these doubts. These are very important concepts which really helps you to clear your basics very well for Hadoop. All right. So this completes, Ilayaraja, this video which I am right now talking. This video you should get. This will be anyway recorded, right? So you will get it from Simply Learn. They will send you this WebEx recordings, so you can rewatch this video. All right. So we have completed writing one block. So I hope everyone is fine now. I have repeated this. So any more questions anybody has on this flow? All right. So let's start understanding how does it write the second block. Remember, we have not yet discussed about second block. So let's understand how does it write data into the HDFS. So what happens is, I'll write it in a different color so that you'll understand. So it will basically create one more data queue and acknowledgement queue instance and one more data streamer instance, data streamer 2. Okay. And here it puts all the packets from second block into this data queue. So data streamer 2 will start picking one packet from data queue and start going to the name node, get those information about which data node it should write the data, and it will also parallelly start connecting to this data node. It could be data node, let's say 4, 5, and 6, or it could be the same data node which was basically chosen for writing the first block. It is possible that name node can give him the same list of data node where data streamer 1 also writing the data. So it is completely possible that multiple threads can write two files parallelly into the same machine. As long as you are writing two files, there is no problem. Okay. And then likewise, all the cycle happens where it takes one by one all the packets and it generates this file with, let's say, new block ID into this machine. So whatever we have understood in detailed manner for block 1, that will be repeated for block 2 as well. All the packets will be written in this file. All right. So you can just visualize that this is how parallel flow happens. Right. So the reason why I have explained in this manner, because the data streamer will always write the data in the parallel manner. Right. So your block writing, this is block B1, this is block B2, assume that way. So block writing is always parallel because there are multiple threads created to write the blocks parallelly into the Hdfs. But packets within the block is sequential. All right. It will take its own time to write the data into the Hdfs. So basically, all the blocks will be written parallelly by these data streams, and that's why you can improve the write performance, because multiple blocks can be written parallelly. However, packet within the write will be written sequentially, as we discussed, because of any failure happens during writing any packet, then data streamer exactly know which point, which data node it fails. And that is what I'm going to cover in the failure scenario. All right. So is everyone clear with this second block information? How does the data gets written into the second block? All right. So what we can do is now, the failure scenario is something that we want to discuss now for this write architecture. But I think before we discuss failure, because failure scenario is also very detailed session, and that also needs a lot of discussion that we need to have. There are different types of questions that would arise in failure that I will cover. Three important questions which we need to cover in failure scenario also. So what we do is, I think it's a good time that we can take a logical break here. We'll come back after the break and then we'll continue further. All right. So is that fine with everyone? Let's take a break now. We'll come back after the break and we'll continue further. We'll take a break of 15 to 20 minutes. We'll come back and we'll start. All right. So see you all after the break. All right, everyone. So let's get going. So we understood the happy path scenario, right? And we also understood how does two different blocks can get written parallelly by multiple data streamers. So we need to just remember that block writing is parallel and packets within the block is sequential. Block writing is parallel and that's how it improves the performance by writing the blocks to the Hdfs. Yes. So block writing is parallel and that's why it is improving the performance of write operations. Now we need to understand what happens in case of any failures. So let me start. I'll just quickly redraw this architecture where we need to understand the failure part. Just give me 1 minute. I'll redraw it. Okay, so we are, let's say, assuming that we were writing these packets. We have written some of the packets, okay, under block 1 as we discussed. Okay, so this is the file under name node has given us the block information. Block 001, let's say. Okay, and it has said that the 001 block is available with data node 1, 2, and 3. And we have also assumed that we were in the process of writing the data. 3 packets are written successfully. We are now writing 4th packet. So let's assume that 4th packet is written into the block 001 in data node 1. Then data node 1 will send a signal to the data node 2. At that time, when data node 2 will basically start writing a packet, assume that it is, let's say, writing some portion of the data, and then it has not yet completed writing packet P4, and then let's say data node 2 fail. Okay. When data node 2 fails during writing the packets into the system, what happens here? In this case, basically, if the data node 2 fails, then it cannot write the complete packet. At the same time, it cannot even send the acknowledgement back to the data node 1. It cannot send request to data node 3, as well as it cannot send acknowledgement back to data node 1. So when data node 1 does not receive any acknowledgement from the data node 2 in a given timeout period, it will basically go and update to the data streamer saying that the packet writing is failed, packet P4 is failed. When the data streamer gets that acknowledgement from data node 1, it will remove this packet P4 and put it into the top of the data queue. It will put the packet P4 again back into the data queue at the top of the data queue. Why? Because since it is failed, it has to be rewritten again. And at this time, since it was failed, data streamer will also update name node saying that this particular packet was failed while writing the data. So what name node does, it will basically give the information to data streamer saying that, okay, by the way, name node, when data streamer updates, data streamer will not say that packet writing is failed, because name node is not aware of any packets. Data streamer will say that block 001 itself is failed. So what name node does, immediately when it gets this information, it removes this block ID from the metadata and it creates a new block ID. Old block ID information is removed from the metadata. It creates the new block ID, and it will basically be, let's say, stored in this fashion. And then name node will send that information back to the data streamer that now you start writing the packets within the new block ID. Now you may have a question that why new block ID is needed. If you have that, just hold on to that. I'll explain you why new block ID is needed. Right now, just hold on to that. So that is about new block ID. Now, once the new block ID is given, data streamer will basically start writing the packets into the data node 1 under a new block ID. Under the file, it creates as a new block ID and basically starts writing the packet. So what happens again? Data streamer will start picking up the packet before again to write it further, put it in the acknowledgement queue back, and start rewriting it again into the available list of data nodes. So it will start writing it into data node 1. In that case, already P4 is written. So what it does, it overwrites it renames the file as block 002 with the new block ID. Then data node 1 will send a signal to data node 3 saying that you also write this packet. So data node 3 will rename the file from 001 to 002 and write packet P4 here. Once that is completed, it will send an acknowledgement back to the data node 1 saying that I am also done. Data node 1 will send an acknowledgement to data streamer saying that you are also done. And that means packet P4 is removed from the acknowledgement queue. Now this cycle continues till all the other packets are written. So P5 and whatever, P6, P7, P8, all the packets are written successfully in these two available data nodes. and that's how this entire block writing will be completed. Now there are a couple of questions which we need to answer in this flow. First is why new block ID is given. Second is, if you observe here closely, the block 002 has been created only 2 times. Even though replication factor is 3, I was able to create only 2 copies successfully because one machine was down. So how do we take care of that? Who will take care of creating extra copy? Who will take care of basically managing the replication factor? That is another question. And the third question, if you can observe here, what happens to this corrupt block? Who will manage this corrupt block? Okay, so I will come to all these 3 questions one by one. But am I audible, everyone? Okay, fine. So let's continue now. Let us answer those questions one by one. The first question is why new block ID is given. Okay. Okay. Before that, I think let us answer this question, which is what happens to the replication factor for block 002? We understood that block 002 has only been copied 2 times into machines. Then what happens to the extra copy? So during the write architecture, these processes will not take care of writing the data in this fashion. Right. So basically, write architecture, when you're writing the data, when you're writing the block in data nodes, it will not take care of creating an extra replica copy. It will just create the copy into the available data node. That's it. But later on, after the architecture completes, there is a separate process available. Yes, Divakaran, that's a correct understanding. All right. So yeah, I was just mentioning that there is a separate process running called Hdfs Balancer. So this Hdfs Balancer will be basically the one which actually does a lot of activities. This is a separate process, daemon process running inside a name node machine. What it does is it will try to normalize the replication factor. Okay. It will basically help you understand, like what it does is, let's say, it keeps on going through all the metadata information of name node and identifies which blocks are there which are having replica copies less than the number of replication factor. So for example, it finds out here that block 002 is created only in 2 machines. That means it has only 2 copies. But the default replication factor is 3. That means this block is having lesser replica copy than the available. So it basically treats them as a under replicated blocks. Okay. And when you have some block is under replicated, then client will basically, I mean, not client, but Hdfs Balancer will basically get the information advice from name node that where do you create extra copy. Name node can ask him to create in any other data node available like DN4, DN5 or any other data node, and then it will create an extra copy, and that's how it normalizes the replication factor. Okay, so Hdfs Balancer, who is a daemon process running in name node machine, who will take care of normalizing the replication factor in a separate process. That is not part of RAID architecture. Okay. Now, so Nikhil, what happens here is basically, see, we have just 2 copies of block 002 available. So in that case, I'm just repeating what I have just said. So basically, you have just 2 copies available for block 002. After your write architecture is completed, there is a process called Hdfs Balancer running inside a name node, which will check like how many blocks will have a less number of copies compared to the replication factor, which is 3. And that those blocks are treated as under replicated blocks. So now it has to create extra copy, right, for that block. So to create an extra copy for that block in one of the data node, it needs to know that information from name node. So it goes to name node. Name node will tell him that these are the areas, or these are the data nodes available where you can go ahead and create an extra block. Once it gets that information, it goes and creates it. So that's how it normalizes the replication factor. Is that clear, everyone? Nikhil, is it clear? Okay. That's about first question. Now, the second question is why we need a new block ID. Why 002 has been given instead of 001 only. So if we want to answer that, let us assume that we would have never got a block ID as 2. So what I'm trying to highlight a point is, let us assume that we got, instead of 2, we got 001 only. Okay. So I'll just repeat what I'm saying. Basically, it was 001 only. You have DN2, DN3. This is also 001 only. Okay. And assume that it has written all the packets in 2 machines completely, right? So once your flow is completed, let's assume that you have written the entire block. 2 machines would have this 2 blocks copies are created successfully. And after that, let's say some client wants to read this file after the file is written. So client will definitely go to the name node, right? He will check with name node that I want to read the file F1. Name node will check that, okay, this file has block 001 with me. Now in between, before client reads the file, let's say this data node which was down will come back again and start sending a heartbeat signal to name node. So now name node will think that yes, this is live node and I can assign him a task, right? So client, when he goes to name node to read a file, name node will check how many blocks are there. It says 001 is there. 001 is available in DN1, 2 and 3. But because client is asking, the DN2 seems to be closer. So name node can ask client to directly go and read it from data node 2 machine. In that case, what happens? It will get the same block with same name but it is a corrupt block. It is a partial data. So client gets to read a partial data. Okay. So to avoid client from reading a partial data, you will need a new block ID. So that yeah, so that name node will never be aware that there is a block 001 information available in metadata. So name node will never be able to give it to the client to read data from block data node 2 for block 001 because that information name node does not know, right? So we are safe in that case. So client will never get to read any inconsistent or corrupt data. That is the reason why we need a new block ID. That clear with everyone? Any doubts? No, Nikhil, I have taken an assumption that why we need a new block ID, that for that we have taken an assumption that what would have happened if new block ID was not given. So we have taken an assumption that old block ID was only present. And in that case, what would have happened, right? It's like proving a math theorem. If you want to prove something as true, you take first assumption that that is false and then, do all the operation and then you say, hence it is true that this is proved. So that is why we have just given you an example that what would have happened if old block ID was maintained. Then client can get to read a corrupt data from that block which is partially written because all the three machines will have the same block name. But since one of the data node which was failed which comes back again, client may get to read that corrupt block, and that's why it is not advisable to have the same block ID, to keep the same block ID. So name node will creates a new block ID and rename those files. So name node will never aware of this old block ID which is a corrupt block, and hence it will never be able to give that information to client so that client can go and read that data. So it is all about making sure that client will never get to read the partial data. That is why new block ID is given. Yes, Shiva, it is absolutely possible. So Raghu, as you understand, right, we are renaming the file. So there is no block 001 exist in DN1 and 3. It was already renamed. Yeah, Vishal, I'm coming to that. What happens if the faulty data node comes back again? So Mano, if the machine fails, you restart the machine, right? So admin will go and fix the failure and restart the machine. That's how name node, data node comes back again. Okay. Now let us assume that you have written all these things, everything is fine, the data node 2 comes back into the cluster. And then let's say when the data node comes back into the cluster, what happens? It is not failed anymore. It is come back in the cluster. So it starts sending a heartbeat signal to name node, right? Now here I think someone has asked me a question that I think Vijay has asked this. So why 10th heartbeat it gives a block report? What was the reason? So Vijay, I'm taking that question here now. See, data node sends a heartbeat signal every 3 seconds to name node, and that's how name node knows that yes, this data node is alive in the system. But every 10th heartbeat, this data node will send a block report to the name node. What do you mean by block report? It will tell that these are the blocks I have with me. So data node 2 also starts sending that block report, and it will say that I have block 001 with me. Now once name node gets to know that okay, data node 2 has this block 001 with him, then name node will check in its metadata whether that block related information is available or not. If the block information, the block ID is not present in the Hdfs, right? So yeah, what I was I'll repeat what I was saying. Basically, when the data node 2 sends a block report, if it says I have block 001 with me, and if it sends that block report to name node 2 will check in the metadata whether the block 002 block 001 exists or not. If name node does not have that information, and it doesn't have because it has already removed that information while when it was failed. So name node does not have any information about the old block, which was a partial block. And then when data node 2 says that I have this block, that means name node treat that block as a corrupt block or a partial block. It will treat it as an orphan block. It says you are saying you have this block, but I don't know any information about that. That means there is a corrupt block, and it will ask Hdfs Balancer to go and physically delete this corrupt file from the local file system of data node 2 machine. That's how these faulty blocks will also be handled. Okay, so this completes all the 3 questions that we wanted to cover for failure scenario. Is that clear with everyone? Any doubts? So Vishal, again, all of these are internal. That means it will be automatically removed. There is no manual process here, which developer has to do anything with. Okay. So Hdfs Balancer will periodically running as a daemon process, and it will go and physically remove it as and when it is told by name node. It's all internals. Okay. If it is clear, please acknowledge. You mean to say, Vishal, 3 replications will take a lot of hard disk space? Is that what you are saying? So in that, yeah, that is obviously given, right? So see, it's like it's about cost of memory, cost of storage versus high availability of the data. So any distributed file system which you go and work will always try to give you higher reliability, and Hadoop will always give you higher reliability. That means high availability of the data, even in case of failures in the system. So to achieve high availability of the data, you need to have a replica copies created for those blocks that you are storing. If you don't have replica copies, you will lose all your data if one machine goes down. Correct? So that's why basically our replication will be maintained. So by default replication factor is 3. That means even if you have 1 terabyte of data, you are going to occupy 3 terabytes, but which is fine, which is absolutely normal. It has to do that. Otherwise, it will never give you, that data availability. Yes, Ilayaraja, that is right. Commodity hardware it uses. I think Vishal, you did not understand the flow, I guess. You are saying at the end of the successful completion of the task, who deletes the file? Where is the file and why do we need to delete the file? The whole point is we are basically storing the blocks, right? These are all files. So we don't need to delete the files. If we want to delete the files, then why to write it on the first step, right? Basically, when we write the file, or when we write the file into Hdfs, it will be divided into multiple blocks. That blocks are meant to be stored actually, so it cannot be deleted. It should not be deleted, right? It will have 3 copies, so that when next time client wants to read the file, it will actually get it from any of the available data nodes. So I mean, it absolutely doesn't make sense to delete the file. If you are writing it, it will be stored. Okay. When you are storing the blocks in data node, that itself means it's HDFS. So understand this part. This is very, very crucial. I mean, that is why I explained DFS first time. So basically, see, this file was divided into multiple blocks, and you are also saying that this block is available in these data nodes. This is the metadata information name node has. Now, as a user, what we know? We know that entire file is stored in this location, but this is just a virtual path, which means it's a SDFS path. But physically, your data will be stored in these kind of physical files in the local file system of this data node machine, right? So that is what we mean by SDFS overall. So SDFS is just a virtual file system. When you store anything in SDFS, internally it will be divided as a physical blocks only. Okay, any further questions anybody has before we move on to the next topic? All right. Cool. So let's go ahead and understand the read architecture. The same way we understood write architecture, we are going to understand read architecture. Read architecture is quite simple compared to write architecture. Okay. So let's say I have already a file written in HDFS, and I'm going to write this command to read the file. Hadoop fs -cat, and I'm going to give the path of the file, data, under that file dot txt. This is the path I'm giving to read the file from the HDFS. So when we execute this command as a user, we are thinking we are going to read the data from this location in the HDFS, but internally behind the scenes it is going and picking up those blocks that we have created in data nodes and then giving you the data. So let us understand what happens behind the scenes when you execute this command. So I'll just draw some boxes. All right. So let us understand that. So what happens step by step? As I said, anatomy of a read is very easy compared to write. So when a client executes this command, behind the scenes, client will make a open method call on the distributed file system object, not the write, but the open method call. Again, distributed file system will know how to talk to name node. He will go and talk to name node and tell name node that there is a client who wants to read a file at this particular location in HDFS. So name node will do that validation and check whether the path exists in HDFS. This time when you want to read the file from HDFS, the path must be present in HDFS, right? So it will check that validation and it will tell you that, whether the path exists or not. If the path already exists, then we are good. But if path doesn't exist, you can't read the file if the file is not present, right? So it will throw an error. Okay. So name node will check about the path information. Apart from that, name node will also do one more validation whether client has a read access to read the data from this location. Once both of these validations are done, name node will give him the control back with some input data about how to go about reading these blocks. So name node, after doing these validations, what it does, it will check in its metadata. As you can see, I have drawn this architecture where there are 5 data nodes, and there is a file which was stored in data node which was in this location. But internally it was divided in 2 blocks, block B1 and B2, and these are available in these 5 machines across. B1 is available in DN2, DN4, and DN. Okay, so here this distribution I have just shown so that you can understand that every block is replicated 3 times into these data nodes. Name node has this metadata information, so what it does, it will just get this information that how many blocks are there for this file and which block is available in which data node, and it gives that information back. Now here, while giving the information back, it will give that this is the block it has, and it will give all the data node location where this block is available. But if you notice here, it will actually do something with that list. It will basically sort the list of data nodes based on the distance between each data node and the client. If the client is near to, let's say, data node 4, that data node will be given first in that list compared to data node 2 or data node 3. Okay. So that is one important information you should remember. So once it basically gives you that block information and the data node location information, right, by sorting this list, DFS is, DFS will basically, it got a return signal from name node with this data. So return type of open method is FY data input stream. So client will basically make a further call to input stream to read the data from the SDFS. Okay. And it already has the data information that these are the blocks I need to read from this file system. Okay. So before we move on to understanding how it reads the data, did we understand about this first flow? Shantanu, it is sorted distance path algorithm based on number of hops. So is everyone clear with this first flow? All right. So now let's understand the next call. So client will make a read method call on fs data input stream object. This time fs data input stream object will have this information like which block it has to read from which data node, and also the data node are sorted, so it needs to connect to only first available data node which should be closer to that client so that it can read the data faster. So what data stream do, it input data stream will basically take the block B1 fs data input stream and then go to the data node 4, and then it will make a physical connection with that data stream. Okay, so yeah, I was just mentioning that it will read block B1, go to the first available data node, let's say data node 4, make a connection with that and start reading the data from there and stream it to the client. It's like streaming the data to the client. Once it completes the reading, it will close the connection with data node 4. It goes to the next available data node and again make a connection with first available data node in that list, stream the data back. Likewise, it completes reading the data one after another. Okay. In case if there is any failure, for example, if it was reading block B1 from data node 4 and if data node 4 fails in between, then what happens? It will basically go to the, let's say if it fails while reading, it goes to the next available data node in that list and it makes a connection with that data node 2, and it starts reading the data from. Alright, so this is how basically the system is going to take care of failures also. It's very simple scenario basically in case of failure also. So this is how the reading happens. Okay. So is everyone clear with this read architecture? Any doubts? All right. So this completes the entire. No, Shantanu, we are already storing replica copies, right? So there is no point of archiving. Okay, so we have completed the entire architecture of read and write. That means we understood how data gets stored and retrieved from the HDFS. Now there is one more topic which is about rack awareness policies, which I'll explain you. So let me explain that part. So this is a rack. I have drawn 3 racks, and each rack can host multiple machines, as you would have seen in the command center or data center of your company, right? So basically, this is all these 9 nodes together will form one Hadoop cluster. Okay, one of them will be a name node, others are data nodes. This is how you can visualize your Hadoop cluster. Okay, now here, see, normally for understanding purpose, you have the name node and data node in this fashion, right? So basically, we have name node here and data nodes are here. This is how we basically understood the architecture, master slave. But actually, this is just for understanding. The actual physical cluster deployment is like this in the rack space. Now, assume that I have a file which I want to store, which has, let's say, 3 copies, block A, B, and C. 3 blocks are created for this file when it's stored in Hdfs. And we also understood that if I store all the copies of block A, if default application is 3 in one rack, in 3 machines of same rack, then there is a high risk, because if this rack fails, I lose all the copies. So still there is a problem with high availability of the data. So it doesn't store in that fashion. In that case, you may assume that Hadoop will basically, in that case, to make it little better, it would basically store it in the all the 3 different machines. So we can easily assume that it would have probably stored it in this fashion. All the 3 copies of block A stored in 3 machines of 3 racks. But there is a problem with this approach also. Let's say if there is a client who wants to read the data, name node will tell him that okay, go and read it from data node rack 2 with machine 4, data node 4. So if he starts reading the block A from data node 4, and what if happens if this machine goes down? Then what client needs to do? It has to go to any other rack and physically connect to that rack and then start reading data from one of the machines. So what happens is basically the the travel time, the network latency is more here, because it has to connect to other rack, then go to that machine and read the data, right? So sometimes even that is possible that racks are set up in different data center in different geographical location. So in that case, it has to travel lot more distance to connect to that data. So in case of failure, network latency is increased and performance will be degraded. To avoid that, Hadoop does not store data in this fashion. So what it does is, it basically, let's say, stores, let's say, 2 copies of block, 1 copy of block in one of the rack, and 2 copies in 2 machines of the other rack. Okay. Now what happens is, when the client wants to read the file, name node will give him that rack first, which has 2 copies, so that if it is reading from data node 7 and if it fails, then it can directly go to data node 9 and start reading the block from there. It doesn't need to it doesn't need to connect to any other rack to read the data from there, right? So network latency is almost nullified here, and even in case of failure, you can read the data faster, right? So this concept is called rack awareness policy. Basically, to improve the reading performance, Hadoop stores data in a much more intelligent manner, and it is aware of the racks and its distribution. That is why it is called rack awareness. So it understands that which 2 machines are part of which rack, and which data node to be given to client when it wants to read the blocks. This is called rack awareness concepts. Is that clear, everyone? Yes, Nikhil. So there are a lot of parameters that are considered while selecting the data node. Distance between the data nodes with the client, this rack awareness concept, as well as load balancing. So there is different priority, right? Depends on so it's like priority will be rack awareness first, then the distance between data node, and then the load balancing. This is the order, right? And which one satisfies, that one will be given first. Okay. Any more questions on this? All right. So what we will do now is, that's what I had for today's session. This completes the entire HDFS architecture and some important topics discussion. Now what we will be doing is we'll be basically starting with a practical in tomorrow's session. I'll explain you how to work with HDFS, how to execute commands on HDFS, and the most important thing is, which I think not many people are aware who are working on Hadoop also, which is how the actual blocks will be created. So what we will do tomorrow is we'll do one exercise where we will create one simple file and in the local file system copy it into HDFS, and then I will show you where the actual physical blocks are created in which location. We will go and open that block and we will see that the data is stored in that block, right? So that will basically validate our concept that we have learned so far, that HDFS is a virtual system. Physically the data gets distributed into the blocks. Okay, so I'll show you that practical also. That will really help you to clarify your doubts also in that. So these are the practicals that we will complete on HDFS tomorrow, and then we will start with MapReduce. Okay, any further questions anybody has? Shiva, Java book is like there are so many Java books available, right? But I would suggest that if you just want to learn Java from the Hadoop point of view, then you can go. In fact, as far as I remember, Simplilearn used to have some Java videos prerequisite for Hadoop. So you, first of all, I would request you to, since you have already enrolled for this course, you can always check with them whether they can give that complimentary videos or not. I remember that earlier, some like 6 months or like few months or 1 year back, they used to give that videos also as a complimentary for the Hadoop session. So you can check with them first. If you don't find it, then I will recommend one book called SCJP, Sun Certified Java Programmer book by Kathy Serra. You just need to learn few chapters from that. You don't need to learn the entire book. Okay. So that is another option. And the third option is you can just you can watch some videos from YouTube on the Java basics. These three options are more than enough to get you the good basics on Java. Okay. All right, in that case, if no questions, everyone, so that's what we had for today's session. So we are done with today's session and we'll come back at the same time tomorrow and we'll continue further. So thank you, everyone. Hope all of you have enjoyed today's session. So have a good day and we'll meet tomorrow at the same time. Thank you. Thank you, everyone. And please feel free to give a feedback once you log off.